So in this chapter, we're primarily discussing factors that affect the stability of intermediates in organic reactions. And in turn, our overall goal is to begin to write reasonable mechanisms for organic reactions, predict regioselectivity for organic reactions, and begin to understand the mechanistic steps involved in common mechanisms that we'll see in this course as well as subsequent organic courses. So to round off our list of different potential intermediate species that we commonly see in organic reactions, we're next going to look at anion stability. Now, this is primarily going to be a review on our chapter 2 notes in this section, but I feel it's important to cover just so that way we have the full context involved and we have all the information at our disposal, somewhat that we've recently covered. So that way, when we move on to start to draw reaction mechanisms, we have this information base to draw from. Okay, so in terms of anion stability, anions in general are more stable on large electronegative atoms. We can see this quite clearly by looking at the pKa's of a variety of acidic protons. And we notice quite clearly that as our atom electronegativity increases, our anion, our conjugate base anion, is more stable. And as a result, the parent acid is more acidic. Okay, so we can use pKa tables as a proxy, as a means of gauging the relative stability of the conjugate base. Because remember, strong acids generate a relatively stable and weak conjugate base. The second major effect that is really important to consider is that if your anion is stabilized via resonance, then your anion is substantially more stable. So if we take a look at the following pairs of anions, we see in the first case for the propyl alcohol derived anion, we see that it's a localized anion, and as a result, this anion is relatively unstable. Compared to the following carboxylate anion, we see that this anion is delocalized via resonance, and as a result, this anion, which is stabilized and delocalized via resonance, is substantially lower in energy and substantially more stable. Do these ideas make sense to everyone so far? You're really going to need to be familiar with anion stability and whether we're dealing with a localized or delocalized charge, and whether or not we're dealing with a basic or a less basic anion, because this plays a huge role when we discuss nucleophilic reactions and other subclasses of polar reactions. Is everyone following along so far? Can I get some feedback that everyone's following along and everyone is sort of remembering what we've covered before when it comes to anion stability? Perfect, perfect. Remember, if you have any questions, don't be shy to ask in the chat. Okay, another factor that plays a pretty big role in anion stability are inductive effects. So remember that electronegative groups adjacent to our anion stabilize our conjugate base anion. So the more electronegative groups we have, the greater the inductive effect, and as a result, the more we can stabilize our anion via electron withdrawing and inductive effects. Okay. The last major effect that we noted for anion stability that plays a pretty significant role in terms of anion stability are orbital effects. So in orbital effects, we know that anions are more stable if the lone pair electrons are in a lower energy orbital. Why is that? Well, if we compare, so if we look at a drawing of our nucleus, for example, and we compare our different orbitals, we notice that the sp orbital, which is shorter and stubbier, holds our lone pair closer to the nucleus, and in turn, we can more readily stabilize our lone pair with the nuclear charge. This is why, in general, the more s character we have in our orbital that our anion is located, the more stable the anion will be. Does this concept seem familiar to everyone? Does this make sense to everyone so far? Okay, now the last major effect that is important to consider is this idea of solvation. We'll delve into the impacts of solvation on different organic reactions later on in this class. The solvent can play a pretty significant role in terms of affecting the overall mechanism of the reaction and the stability of different intermediates along the reaction coordinate. So, in terms of solvation, solvation is based on this idea that if you have your solvent, let's look at a theoretical solvent, like for example, ethanol, okay? Now, the less steric congestion we have around our anion, the more stable the anion. The reason for that is that when you have this really bulky anion, this steric bulk prevents, or I wouldn't say it goes so far as say prevents, but it limits solvent coordination. So as a result, we're less able to stabilize our anion. We're less able to stabilize our anion via hydrogen bonding and other effects because we have a substantial amount of steric bulk, which is taking up space and limiting coordination of solvent around our anion. We'll see these steric effects again when we talk about different reactions that are partially facilitated or stabilized via solvation effects. Does this idea look familiar to everyone? This idea of stabilization from the solvent, this idea of solvation effects? Okay. So, now that we've covered a fair amount of review, we're now going to double back and we're going to discuss some critical ideas covered in the general chemistry sequence that we're going to use to help us understand organic reactions and rationalize the mechanisms of organic reactions. Okay, so the first main concept that we're going to discuss is this idea of reaction enthalpy. One moment. Okay, so fundamentally, breaking chemical bonds costs energy, and forming chemical bonds releases energy. So the act of breaking high energy bonds and forming low energy bonds in turn releases energy. So exothermic reactions form stronger bonds or lower energy bonds in the product than in the reactant. And in turn, exothermic reactions release energy. So by comparing the enthalpy of our reactants and products, we can calculate the amount of heat absorbed or released by our reaction. In this case, we're looking in the following graph at an exothermic reaction. Any questions so far? Does this look familiar from Chem 101 and 102? Perfect. Okay. So as an alternative to the exothermic reaction, endothermic reactions break stronger bonds than they make, and they require energy in order to proceed. So in this case, our enthalpy of reaction is greater than 0. So this is a typical endothermic reaction or process. Okay, so now that we've seen two different types of reactions from the perspective of enthalpy, let's talk about some tabulated values that we can utilize to estimate reaction enthalpy. So bond dissociation energy, as we've discussed previously when we talked about radical reactions, measures the amount of energy required to break a given bond to produce two radical fragments when the molecule is in the gas phase. So this is the bond dissociation energy is useful for estimating reaction enthalpy. It won't give us a 100% exact reaction enthalpy because there are some steps that we're well, first because these bond enthalpies can change a little bit depending on your structure, but it gives you a nice approximation for the amount of energy required to break a bond in a radical-like process, and it can be used to estimate the overall reaction enthalpy utilizing Hess's law. Okay, so how can we leverage bond dissociation energies to calculate some meaningful values and get a sense of the reaction enthalpy for different chemical reactions? Well, we know from Hess's law that we can break our chemical reaction process. So let's suppose we're looking at a typical reaction of AB plus CD leads to AC plus BD. So just a typical chemical reaction. Well, we can break this chemical reaction into a series of discrete steps. We can break this chemical reaction into a series of discrete steps. This is the fundamental principle behind Hess's law. And by the same token, we can in turn take any chemical reaction that we're looking at, and rather than tracing along the actual reaction pathway, we can model each of the reactions that we're looking at as a series of homolytic bond forming and bond breaking event. So we can estimate the enthalpy of our reaction by looking at the enthalpy of the bonds broken over the course of the reaction minus the enthalpy of the bonds formed over the course of the reaction. Does that idea make sense to everyone? Does this application of Hess's law look very familiar? So we're essentially modeling our reaction through an alternative path that can be modeled as a series of bond forming and bond breaking steps where we know the enthalpy of each of the bond forming and bond breaking steps. And as long as our starting and end point are the same, we're in turn describing the enthalpy of the same reaction. Okay, so let's show an example of this. So suppose we're looking at the enthalpy of reaction for the combustion of methane. Now it's really important if you're using this method that you accurately and completely draw out each of your reactants involved in each of your products generated. You need to be very careful that you are accounting for all of the bonds broken and formed in this process. So to do that, I draw a picture of each of my reactants and products with each of my bonds explicitly drawn. Okay. So if we know that the enthalpy of reaction is the sum of the enthalpy associated with our bonds broken minus the sum of the enthalpy of our bonds formed. So we see that in terms of the bonds that we are breaking, what bonds are we breaking in this process? What bonds are being broken in this chemical reaction? Carbon-hydrogen bond, yep. And how many of them are there? So we have a bond enthalpy of 414 kilojoules per mole, and we see that we're breaking 4 total carbon-hydrogen bonds. Perfect. What other bonds are we breaking? What other bonds are we breaking? Yep, an oxygen-oxygen double bond, and we're breaking 2 of them. Exactly right. So we take our enthalpy for an oxygen-oxygen double bond, and since we're breaking 2 of those bonds, we multiply our bond enthalpy by 2. Okay, so those are all the bonds that we have broken in this process. Now let's look at the bonds that we are forming. So what bonds are we forming in this process? What bonds are we forming? Oxygen, hydrogen, sure, that has an enthalpy of 464 kilojoules per mole. And how many of those oxygen hydrogen bonds are we forming? 2 per water molecule. And because we have 2 water molecules, 2 times 2 gives us a total of 4 oxygen hydrogen bonds. Perfect, perfect. Now, what other bonds are we forming? What other bonds are we forming? Yep, we're forming a carbon-oxygen double bond, which has an enthalpy of 799 kilojoules per mole. This is the exact enthalpy of a carbon-oxygen bond in carbon dioxide, and as we notice, we are forming 2 of those carbon-oxygen bonds. So if we punch this into our calculator, that gives us an enthalpy of reaction of negative 802 kilojoules per mole of carbon dioxide produced. So as we can see, this reaction is relatively exothermic, and as a result will generate a fair amount of heat. Does this idea make sense to everyone? Does this idea make sense to everyone? Okay, so we can leverage bond enthalpies to estimate the reaction enthalpy, okay? So let's talk now about enthalpy effects, how reactions can, depending on their reaction enthalpy, enthalpy can serve as a quote unquote driving force for many different chemical reactions. It can assist chemical reactions to go to completion. So let's look at some reactions that are favored via enthalpy and as a result can be driven to completion via these beneficial enthalpy effects. So one of the most common reactions that we'll see that is favored via enthalpy are reactions that involve the replacement of weak pi bonds with stronger sigma bonds. So a classic reaction of this type is an addition reaction. In turn, where our alkene attacks is protonated, and we eventually end up replacing this relatively weak pi bond with 2 strong sigma bonds. If you calculate the reaction enthalpy for this quote unquote addition reaction, you will notice that this reaction is exothermic. This favorable reaction enthalpy in turn means that many addition reactions are quite favorable when run at low temperatures. So the main driving force, partially one of the reasons why this reaction occurs so efficiently and readily, has to do with the favorable reaction enthalpy. Now, enthalpy isn't the only factor, but it can certainly benefit and can certainly help make reactions more favorable. Does this idea make sense to everyone? So another example of reactions that are favored via enthalpy are reactions that generate very strong sigma or pi bonds. Probably the most well-known sort of typical strong sigma or pi bonds that we see are a silicon-fluorine bond, silicon-oxygen bond, or a phosphorus-oxygen double bond. These bonds have very favorable reaction. At least these bonds are, when formed, in general, end up with the release of a lot of energy, and forming these very strong bonds is highly favored via enthalpy. So this can often serve as a driving force for many common organic reactions. So for example, a Wittig reaction, one of the driving factors that makes this reaction so overwhelmingly favorable is that we are generating a very strong phosphorus oxygen double bond, which in turn makes this overall reaction enthalpy very favorable. Wittig reactions can often be exothermic if you choose a particularly reactive aldehyde or ketone. Does this idea make sense to everyone? This idea that reactions can be made more favorable if they have favorable reaction enthalpies. And this enthalpy can be driven by forming stable low energy bonds or by replacing higher energy pi bonds with lower energy sigma bonds. Okay, so oftentimes if you're drawing a mechanism, your mechanism should partially account for why the reaction is favorable. And in the case of the Wittig reaction, the key payoff step in terms of energetics is that you're generating this very, very low energy phosphorus oxygen double bond. That helps sort of drive the reaction to completion. Okay, the next factor that we need to talk about is entropy. Now, as we've discussed in Chemistry 102 in your previous courses, enthalpy is not the end-all be-all for whether or not a reaction is favorable. We have to consider both enthalpy and entropy effects. Now, entropy can be thought of as a measure of the disorder present in a system. Another definition that is more commonly used is a measure of the number of microscopic configurations and microstates a system can occupy. I like this second definition since it can help us rationalize and help us more tangibly sort of estimate the relative entropy of different organic systems. Okay, so in general, disordered systems with a large amount of freedom of motion and freedom to occupy different states have higher entropy. The most tangible example I can think of is if we're comparing a cyclic versus an acyclic system. So let's try to rationalize why that is. In an acyclic systems are relatively flexible and they have a greater number of accessible conformations. All of our carbon-carbon bonds are rotatable. If we compare that to a cyclic system, this cyclic system has a limited number of possible conformations. And thus, because the acyclic system has a greater number of accessible conformations and a greater sort of number of accessible orientations and ways that it can arrange itself in space, the acyclic system is considered higher in entropy, or it's considered a higher entropy system. Does that idea make sense to everyone? This idea that if we compare a cyclic versus an acyclic system, the cyclic system has more freedom of motion, more freedom in terms of accessible conformations, and as a result, acyclic systems are considered higher in entropy. Does that idea make sense to everyone? So it's not, they're favored via entropy. And that's the important thing to consider. We have to balance both entropy effects and enthalpy effects. And as we'll see, depending on the temperature of our reaction, we'll either see a more substantial impact from entropy or enthalpy effects. So acyclic systems are higher in entropy, and so they're favored via entropy, but they aren't necessarily favored via enthalpy or other factors. The last discussion that I want to have when we talk a little bit about entropy is this idea of physical states. And this idea stems from this fact that gases are generally higher in entropy than solids or liquids. Gases have a greater number of possible states they can occupy, and as a result, they're higher in entropy. So as a result, when you end up with chemical reactions that readily generate a byproduct gas, so for example, if you're looking at like a decarboxylation reaction, for example, where you in turn generate a byproduct gas, generation of gas is highly favored via entropy. So generation of gaseous products is favored via entropy. Does this idea make sense to everyone so far? Perfect. Okay, so there are a few factors in reactions that can increase the entropy of our system. So the first of which is the generation of multiple products. If we generate multiple products, in general, we have more possible potential states on our product side. We have, and in turn, if we take one reactant and generate multiple products, this reaction is favored via entropy. So we are increasing the amount of entropy of our system. This is commonly seen in elimination reactions, where we take a reactant molecule and after elimination, we generate two product molecules. Notice that this reaction is not necessarily favored via enthalpy, but it is highly favored via entropy. Does this make sense to everyone? This idea that depending on the number of product molecules that you generate, the reaction can be either favored or disfavored via entropy. As we discussed previously, the second major factor that can drive reactions and make reactions favored via entropy are reactions that generate gaseous products. As we noted previously, gaseous species are higher in entropy typically than liquids or solids, And as a result, many reactions are highly favored via entropy as they generate a gaseous byproduct upon completion of the reaction. The most common example would be our decarboxylation reaction, where carbon dioxide gas is a product of the reaction. Okay, so now let's put this together and let's talk a little bit about how we consider enthalpy and entropy effects as a whole. So, the ratio of products to reactants is controlled by the Gibbs energy of reaction that we call delta G. This Gibbs energy of reaction represents the change in the Gibbs free energy between the products and the reactants. So we can model the Gibbs free energy of a reaction using the following equation, where delta H is our reaction enthalpy and delta S is our reaction entropy. One thing that immediately stands out to us, as we've observed previously in general chemistry, is that the Gibbs energy of a reaction is temperature dependent. And as the temperature increases, the entropy term has a greater impact on the Gibbs energy of the reaction. Now, what this means practically is that at high temperatures, reactions that have positive entropy values that result in an increase in entropy become more favored. Further, at high temperatures, reactions that have negative entropy values become less favored. So, as we notice, depending on the temperature of our chemical reaction, the reaction's impact, the reaction entropy's impact becomes more or less pronounced. Okay, so let's look at a practical example of how this works. Let's look at a practical example. So when we discuss substitution and elimination reactions, heating has a substantial effect on whether we observe substitution or elimination. Now, there are two competing reactions at play when we consider a typical substitution reaction. We can either have straightforward substitution where our nucleophile attacks and our leaving group leaves, or as an alternative, if we're looking at the elimination pathway, we have abstraction of a proton and elimination of our leaving group. Okay, so there are two potential pathways at play. It's found empirically that lower temperatures tend to favor substitution. And let's try to rationalize this observed trend using what we've learned about enthalpy effects, entropy effects, and reaction Gibbs energy. Okay, so we know that all else being equal, as the temperature of a reaction increases, more elimination products are observed. So temperature control plays a pretty big impact on this reaction. The more we increase the temperature, the more elimination product we observe. Okay. So let's try to explain why that is. Why does that occur? Well, if we compare substitution versus elimination, let's think about the entropy term. So in substitution, we start with two reactant molecules and we end with two product molecules. So then, would we expect to see a large or small entropy effect? Would we expect to see a large or small change in entropy for substitution? Small, right? We're not really changing the number of molecules before or after the reaction. So we have a relatively small change in entropy, right? We're not generating any additional product molecules. We're not generating any gaseous products. We're not generating a acyclic system compared to a cyclic system. So overall, we don't really see a substantial change in reaction entropy. If we compare this to an elimination reaction, we start with 2 reactant molecules and we end with 3 product molecules. And as we discussed previously, generation of a large number of products, generation of a large number of product molecules, is that favored or disfavored via entropy? It's favored via entropy. So we have a large change in entropy. And this reaction, in turn, is favored via entropy. Does that idea make sense? Does this process of analysis make sense to everyone? Okay, perfect. So now that we've established that elimination reactions are substantially more favored via entropy, that in turn can help us explain this temperature effect. Since remember, Gibbs energy is a function of the enthalpy, entropy, and temperature. And as we notice, the entropy term plays a greater role in the reaction favorability at higher temperatures. So as the temperature increases, the elimination reaction, Gibbs energy, decreases substantially as the entropy term plays a greater role at higher temperatures. What this means practically is that at higher temperatures, elimination becomes more favorable. Does this make sense to everyone? Does this explanation, considering the reaction enthalpy and entropy effects, make sense? Can we rationalize and can we explain why elimination is favored at higher temperatures using this model? Any questions on this method of analysis? Any questions? Okay. So let's continue on now and let's really delve into the Gibbs energy of reaction in detail. So the Gibbs energy of reaction is related to the reaction equilibrium constant, right? So there's a relationship between the standard Gibbs energy of a reaction and the equilibrium constant. This is covered previously in general chemistry, such as in 101 and 102. Now, the equilibrium constant is the ratio of the product and reactant concentrations at equilibrium, accounting for stoichiometry. Okay. So from this information, we can conclude that reactions that are product favored are known as exergonic reactions. Just like exergonic is a term somewhat related to exothermic, except this time it's referring to a Gibbs energy that's less than 0. So in turn, the total Gibbs energy of our products is less than that of our reactants. Exergonic reactions have a standard Gibbs energy of less than 0 and an equilibrium constant greater than 1. These are considered your typical product-favored reactions. For your reactant-favored reactions, these are typically endergonic reactions with a Gibbs energy greater than 0 and an equilibrium constant less than 1. Do these terms look familiar to everyone? So this is just reviewing the relationship between Gibbs energy and the equilibrium constant. Okay, so we're going to focus a lot on the reaction Gibbs energy, but in order to accurately analyze chemical reactions, we have to get a little bit more specific in terms of what Gibbs energy we're looking at. Now, overall reaction Gibbs energy is useful for looking overall at whether a reaction is reactant or product favored. However, if we're concerned, as we are in organic chemistry, with which products are favored in competing reactions, we have to look at the transition states for the different competing reaction pathways and the activation energy, which is written as the Gibbs energy of activation. Okay, this is different than your overall reaction Gibbs energy. We're looking at our different transition states, and we're now going to delve into the activation energy for different chemical reactions. Okay? So let's do just that. So let's look at a typical reaction pathway, and let's sort of talk about how we can understand what's going on in a typical chemical reaction. Okay, so first and foremost, if we're looking at a reaction coordinate, so this graph is known as a reaction coordinate, and it describes the energy of our different reactants, products, as well as intermediates, including the transition states, as a function of reaction progress. Okay. Now, looking at this reaction coordinate, the highest energy point in a reaction step is called the transition state. Okay, so we have our reactants, we have our products, and the Gibbs energy of our reaction, or delta G reaction, is the difference in energy between our reactants and products. As we see in this case, our Gibbs energy of reaction is greater than 0, so this is an endergonic reaction. Okay. Now, the transition state is the highest energy point in a reaction step. So in our conversion from reactants to products, we go through a transition state. And the difference in energy between our starting reactants and our transition state is known as the activation energy. And the activation energy plays a critical impact on the rate of the chemical reaction and the selectivity for different chemical reactions. Now, keep in mind that the activation energy, in this case, we're looking at the activation energy to go from the reactants through the transition state to the products. However, reactions can be run in both directions. Reactions can be reversible. So we can also look at the activation energy if we were to go from the products to the reactants. So this is the Gibbs energy of activation for the reverse reaction. And by comparing the activation energy for our forward and reverse reaction, we can actually begin to estimate the equilibrium constant for this reaction. Does this make sense to everyone so far? How we've labeled this reaction coordinate, how we've identified the transition state as the highest point in a reaction step, as the highest energy point in a reaction step. The activation energy is the amount of energy required to reach the transition state. Note, we have to look at the activation energy for the forward and the reverse reaction. And by looking at the activation energy of the forward and reverse reaction, as well as looking at the overall energy of our reactants and products, we can estimate the equilibrium constant for our reaction. Does that idea make sense? Does this analysis make sense to everyone? Any questions so far? Okay, so let's keep going now. So in this case, we're looking at, in this reaction, we're looking at a typical addition reaction where the first step entails attack of the alkene to generate a carbocation. We are just looking at, in the reaction coordinate, this first step. Now, I always want you to keep in mind that reactions are reversible, and the reverse reaction can proceed through the same intermediate or transition state. Okay, so let's continue our analysis. So the activation energy is intrinsically tied to the reaction rate. Now, the activation energy and the reaction rate are directly related through the Arrhenius equation, where the rate constant is a function of the activation energy and the temperature. And because this is an exponential term, minor changes in reaction activation energy and minor changes in temperature can result in dramatic changes in reaction rate. Now, one consequence of this equation that we can readily note is that the reaction pathway with a smaller activation energy will occur faster, and more product from that pathway will be preferentially generated in most cases. Okay, so in this case, we're looking at a full reaction coordinate for an addition reaction. So we have two discrete steps in our chemical reaction. We have two discrete steps. And each of these steps each have an activation energy. So in the first step, we are looking at the addition and protonation of an alkene to generate a carbocation. That is our first step. That's what we're depicting here. This first step has a Gibbs energy of activation, and we can look at the activation energy for this step. Okay. This first step has a transition state that I'll call transition state number 1. And after passing through the transition state, we generate an intermediate that I'll call intermediate number 1. Now, a transition state and intermediate are different terms. An intermediate is a species that is isolable and observable over the course of our chemical reaction. Depending on how stable the carbocation is, you can even potentially isolate and directly observe a carbocation. The transition state is a fleeting, the transition state can best be described as a fleeting species, and it is describing how our reactants are organizing themselves in order to complete the bond forming or bond breaking event for that step. Does that idea make sense to everyone? So an intermediate can be isolable, observable, while a transition state is looking at how the reactants are coordinating, arranging themselves, and engaging in bond forming and breaking steps in order to reach your products. Okay, so we've looked at the first step. Now looking at the second step, as we notice, the second step has a second transition state that we'll call transition state 2, and a second activation energy that we'll call the Gibbs energy of activation for step 2. Now, for this multi-step process, for this multi-step reaction, where in step number 2, we're just looking at attack of our carbocation by our nucleophile. What's really important to consider is that in terms of reaction selectivity and the selectivity and rate of a chemical reaction, the selectivity and rate of a chemical reaction is controlled by what is known as the rate limiting step, which is the slowest reaction step with the largest activation energy. So in this case, in this multi-step reaction, which step would be our rate limiting step? Which step has our largest activation energy? Which step is our slowest step in this reaction? Step 1 or step 2? Which step has the largest activation energy? The largest difference in energy between our reactant or intermediate and our transition state? Step 1, yep, exactly right. So step number 1 is rate limiting. And a consequence of that is that step 1 is also going to be selectivity determining. So the rate limiting step plays a critical role in controlling not only the rate of reaction, but the product selectivity of that reaction. Now, this is important to keep in mind because this can help us explain the preferences for these different reactions and explain why some products are generated preferentially over others. Does that idea make sense? Does this idea of looking at multi-step reactions and identifying the rate limiting step, does that make sense to everyone? Okay. Okay. And the rate limiting step, as we've talked about, controls the product selectivity for a reaction. Okay, wonderful. Well, how can we describe different reactions, and how can we talk about the products generated from different reactions? Well, reactions can produce different products depending on the temperature, reaction enthalpy, and reaction entropy. So we can describe products as either kinetic or thermodynamic products. So the kinetic product is defined as the product generated from the faster reaction pathways with a lower activation energy. Note, when we talk about kinetic and thermodynamic products, we are looking at activation energy. Which product is generated is based on activation energy, not overall Gibbs energy. So if we look at the pathway in green, we see it has the following Gibbs energy of activation, right? The pathway in green also has an overall reaction Gibbs energy as shown. Now, what do we care about in terms of reaction favorability? What do we care about in terms of reaction rate? Do we care about the overall Gibbs energy or the activation energy? What determines the rate of reaction? Activation energy or overall reaction Gibbs energy? The activation energy. So for our kinetic product, the kinetic product is described by the product generated from the pathway with the lower activation energy. The reaction pathway to generate our kinetic product occurs more readily because it has a lower activation energy. So even though our final product has a higher Gibbs energy, that doesn't matter in terms of product selectivity because the reaction to generate our kinetic product occurs more readily because it has a lower activation energy. Looking at this second case, we see that the activation energy for our second reaction, is it larger or smaller? So for the second reaction pathway in red, is our activation energy larger or smaller? It's larger. So this second pathway would be a slower reaction. However, if we look at our overall Gibbs energy of reaction, we see that we generate a more stable intermediate. We call this reaction product the thermodynamic product. And the thermodynamic product is the lower energy product. Note that the kinetic and thermodynamic product are not always different products. Now, further, whether the kinetic or thermodynamic product is favored is highly dependent on the reaction temperature. And it's key to identify if a reaction is being run under kinetic or thermodynamic control. And that is highly dependent on the temperature that you're running the reaction. So does this idea of kinetic and thermodynamic product make sense? Does this idea of the kinetic and thermodynamic product make sense? Now, depending on the temperature that the reaction is run at, this activation barrier can play a larger or smaller role. If you run the reaction at a higher temperature, in general, you begin to see more equilibration, more reversibility, and you can start to funnel towards the thermodynamic product. This only really occurs at high temperatures where you see a significant amount of reversibility. We'll talk more on that a little bit later. So, looking at the Arrhenius equation one more time, at higher temperatures, the activation barrier is more easily surmounted, and the kinetic product can undergo a reverse reaction. Then it can undergo a forward reaction through the higher energy path to generate the thermodynamic product. The kinetic and thermodynamic product can be interconverted under what are known as equilibrating conditions. So at high enough temperatures and under the correct reaction conditions, you can actually convert your kinetic product into the thermodynamic product. Note, this is a relatively slow process, and you may still see a little bit of your kinetic product still remaining. But the key thing I want you to keep in mind is at higher temperatures, this activation barrier is more easily surmounted. And as a result, you can see more reversibility and funneling towards the lower energy thermodynamic product. Does that idea make sense to everyone? Okay, perfect, perfect. So what we're next going to talk about is what I would consider one of the most important concepts in terms of analyzing a chemical reaction and predicting product selectivity. And it is known as the Hammond Postulate. So the basic principle behind this postulate is that the structure of a transition state resembles the structure of the nearest stable species. So transition states for endergonic steps structurally resemble products, while transition states for exergonic steps structurally resemble reactants. Okay? In other words, the transition state is similar to an intermediate reactant or product that is close in energy to the transition. Okay. So, with that definition presented, let's talk and let's look at different reactions. So, as a review, an endergonic reaction has a Gibbs energy of reaction greater than 0. And as a result, following the Hammond postulate, our transition state would resemble our products in terms of structure. So, by extension, by looking at our different possible products, we can compare the energy of our possible products and in turn relate the relative energy of our products to the relative energy of our different transition states. Okay, so let's show how this can be applied. I'd like you to turn your attention to this graph on the right. Okay, so we clearly see that this is an endergonic reaction, right? Our Gibbs energy of reaction is greater than 0, right? Does everyone see that? Okay, so as a result then, we're going to compare our two products. So this is going to be product 1. And as we see, product 1 is higher in energy, right? Product 1 is directly related to transition state number 1. Now, following the Hammond postulate, the transition state resembles the closest energy reactant or product. Since this is an endergonic reaction, our transition state resembles our products. So it resembles product 1, and as a result, transition state number 1 is higher in energy. Does that make sense to everyone? Endergonic reaction, transition state resembles our products. Product 1 higher in energy, transition state 1 is higher in energy. Does that make sense? By the same token, if we look at product 2, which is lower in energy, because our transition state resembles our product, if we're looking at transition state number 2, would we expect it to be higher or lower in energy compared to transition state 1? What would we expect? Okay, so let's unpack this one more time. So the Hammond postulate states that the transition state resembles the species closest in energy, right? So for an endergonic reaction where our Gibbs energy is greater than 0, our transition state will resemble our products, okay? So in this case on the right, we're looking at a set of endergonic reactions that generate two different products, right? Now, as we noted, because this is an endergonic reaction, the energy of our transition state will resemble the relative energies of our products. Now, as we noted, product 1 is higher in energy than product 2. So then, would we expect transition state 1 to be higher or lower in energy than transition state 2? Which transition state would be higher in energy? We would, as students are noting in the chat, that transition state 1 is higher in energy because it resembles the product 1, which product 1 is higher in energy. Okay, so product 1 is higher in energy, transition state 1 is higher in energy. Product 2 is lower in energy, transition state 2 is lower in energy. So then, based on this idea now, if we look at the Gibbs energy, if we look at the activation energy for these two reactions, which of these products is the kinetic product? Which product has the lower activation energy? Which product has the lower activation energy? Product 2, exactly right. So product number 2 is the kinetic and thermodynamic product. So as a result, this reaction, if it's run under kinetic control, will typically favor to generate product 2 preferentially over product 1 because the activation energy is lower. Does that make sense to everyone? Does that idea make sense? Any questions on this example? We'll be doing more examples like this, but it's important that we tackle the endergonic and exergonic cases one at a time, and we don't mix them up because they have slightly different ways of handling them. Okay, so we've covered the endergonic reaction where our transition state will resemble our products. Now, we're next going to look at the exergonic reactions. Exergonic, like exothermic, the Gibbs energy is less than 0, and in this case, our transition state resembles our reactants. Okay, so for exergonic reactions, our transition state resembles our reactants. Why? So if we think about our reactant compared to our transition state, which is closer in energy to our transition state, the reactant or the product? What is closer in energy to the transition state, the reactant or the product? The reactant, exactly right. So the transition state resembles the reactants as they are closer in energy. Okay, so our transition state resembles our reactants. Okay. So with that established, let's look at a variant. Let's look at a variant So we're going to look at a series of curves, and let's show what would happen if instead of looking at an endergonic reaction, we are looking now at a series of exergonic reactions. Okay. So we've modified this drawing slightly. We've modified this drawing slightly. And now we're going to analyze and we're going to compare and we're going to look and see the major differences between an endergonic and an exergonic reaction. Okay, so let's unpack this exergonic reaction. So in this drawing, we've now noted that this is so by adjusting these curves a little bit, we're now looking at an exergonic reaction where our Gibbs energy of reaction is less than 0. And as a result, our transition state will resemble our Let's look at the exergonic reaction on the next page. Let's look at the exergonic reaction on the next page. We'll do an analysis of an exergonic reaction. Let's draw out one on the side, just so that way we can compare versus, if we compare and contrast an endergonic versus an exergonic reaction. So here we have a typical endergonic reaction. Let's draw out an exergonic reaction coordinate on the side, just as a side-by-side comparison. So if we're looking at an exergonic reaction, so we're going to draw two lines for A and B. So we have coordinate A and B. Okay, perfect. So in an exergonic reaction, just showing you how you'd put together one of these curves on your own, your transition state resembles your reactants. Okay, so then if we compare A and B, which species, which reactant is higher in energy? Which reactant is higher in energy? If we compare A and B, we note that A is higher in energy, and as a result, the transition state for A is higher in energy. Okay, so this is what a typical pathway would look like for pathway A. Comparatively, because reactant B is lower in energy, it in turn would have a lower energy transition state. Now, what's really interesting, and the reason why I wanted to draw out a sample reaction coordinate, the reason why I wanted to draw out a reaction coordinate is that if we look at product A, what would we call product A? Is product A a kinetic or thermodynamic product? Is product A a kinetic or thermodynamic product? So if we compare our activation energy, so So if we compare our activation energies, which of these reaction pathways has the larger activation energy? Which of these reaction pathways has the larger activation energy? A, right? So we know that the activation energy for A is going to be greater than the activation energy for B, because the transition state for A will be higher in energy because reactant A is higher in energy and the transition state resembles our reactant. So as a result, for pathway A, if it has the larger activation energy, pathway A is less favored. However, even though A is not favored kinetically, what do we call the product that is lower in energy? What do we call the product that is lower in energy? So A is the thermodynamic product. So A would be called the thermodynamic product. While product B, what would we call product B? What would we call product B? B would be called the kinetic product. Does this idea make sense? Okay, so let's unpack this step by step. Let's repeat this one more time, just so that way we are 100% clear. So we're looking at an exergonic reaction. Gibbs energy of reaction is less than 0. If we compare pathways A and B, for an exergonic reaction, our transition state resembles our reactants, right? Since reactant A is higher in energy, the transition state for pathway A would be higher in energy. So the activation energy for pathway A would be higher. That in turn means that if we think about our product selectivity, we know that product B is preferentially formed. And the reason why product B is preferentially formed is because the transition state is lower in energy. There's a lower activation energy because the transition state for B resembles the lower energy reactant B. So because of that, we see for this reaction, B is the kinetic product. It's favored in terms of the pathway having a lower activation energy. A is known as the thermodynamic product because even though the pathway has a higher activation energy, product A overall is lower in energy. Does that idea make sense to everyone? Does that idea make sense? So as we notice, it's really important to be able to identify whether your reaction is endergonic or exergonic, because the method of analysis and the overall what your transition state will resemble, whether it resembles the reactant or product, directly depends on whether your reaction is endergonic or exergonic. So the first thing you have to do whenever you look at a reaction coordinate is identify whether it's endergonic or exergonic. Once you have that established, you can begin to compare the transition state energy, and then from the transition state energies, you can estimate your activation energies, and in turn, estimate which product is preferred. Notice that if we put this endergonic and exergonic reaction side by side, if we put these two reactions side by side, we notice that because one reaction is endergonic and the other reaction is exergonic, even though the reactant and product energies in both of these diagrams are drawn very similarly, because the reaction on the right is exergonic, the selectivity for the reaction is substantially different. Does that idea make sense to everyone? So you really need to be very careful when classifying your reaction, because subtle differences in your reaction Gibbs energy can result in large differences in your product selectivity. Any questions on this example? Any questions on this example? So that's all I have planned for this lecture session. I know that